Hi everyone, welcome to Meltwater. I think a few of you, at least, are familiar faces that I've seen before at similar events. I wanted to start by asking a couple of questions just to get a feeling for how I should do the talk. How many of you here are engineers or have engineering background? All right, perfect. How many of you have computer science background within engineering? Perfect. Okay, so good. I think the level at which I've made this talk is not going to be too high. It might even be boring for some of you, but it will be a good level, I think. There's a few equations and stuff in there. Don't get scared. I'll speed through those. All right, let's get started. This is the outline of my talk. I'll give you a quick company background and what data science and in particular NLP means at Meltwater. I'll talk a little bit about what the challenges of NLP technology, natural language text processing is at large scale. And then, of course, the sort of meat of the talk will be entities, and I'll talk about what's called named entity recognition on the social domain and entity level sentiment. And if there's enough time, we'll see how many questions and stuff there is. I'll say a few words about the knowledge graph. All right. What is Meltwater? So Meltwater is a Norwegian company originally. It was founded in Oslo as, at the time, a media monitoring company. Its core business has always been to analyze news, blogs, and as of the past couple of years, of course, social media for the benefit of customers who are looking for insights from the outside of the firewall. So traditional ERP, CRM systems, of course, look at the data that's within the firewall, the company data, the business intelligence data, and try to deduct sort of advices and insights for the decision makers of the company. What we do is that we do the same thing in terms of providing business insights, but based on the data outside the firewall. And our core philosophy is that the data outside your firewall, the data that's outside your company, is far more important for your business and your business decisions than the data inside. Our founder and the CEO is Jorn Lisegen, who started the company out of a garage in Oslo with 3 guys and grew it bootstrapped. It wasn't until a couple of years ago that we took in VC, so bootstrapped up to $200 million in revenue. We're about 1,000 employees in 30 countries, 60 offices, all from that initial garage project and I think $10,000. And our tech offices are a bit more concentrated. Most of the offices that we have are sales offices. And what is it? Why are the insights that we provide relevant? Why are we providing this service at all, right? Of course, the informed decisions is at the core of it, and your own brand is something you definitely want to monitor out there. Your competitors is another thing that you want to keep track of. Your own industry in general. You can use it to find leads, right? You want to keep track of partners and how they're doing. Your products, how are they doing out there in media? All of this are the components of what we call informed decisions. And we believe that when a decision maker, an executive comes to work in the morning, they should have everything they need to know that day in terms of everything outside of the world outside in order to make informed decisions. We call it the morning coffee informed decisions. Here are a couple of examples of customers. besides the big ones, the big names that, like Coca-Cola, BMW, IKEA, these are the more interesting cases, in my opinion, of use cases of our technology. For instance, Securitas uses Meltwater to find out about new instances of vandalism and break-ins. Obviously, being a security company, surveillance company, that's important because often those victims are in need of their service, right? Lead generation. Sanofi, which is a patent technology company, uses us to be alerted of when certain patents in target markets will expire. Goldcorp, gold mining company, uses Meltwater social listening to estimate and prevent infrastructure attacks, actually. Kimberly-Clark uses us to help determine how public perception of their drugs is trending or evolving. And the Indian news channel NDTV uses us to monitor performance and popularity of news anchors. So this is just a few examples amongst our 30,000 clients of usages of our service. How do we do this? Well, we do it through this dashboard. It's a fully configurable dashboard where all sorts of data inputs, so these news, these blogs, these social media channels, can be represented in terms of graphs, where the analytics that we do on these channels can be very easily digested. Again, hopefully with the morning coffee. I won't talk too much about our product and the values of it. You're not here to listen to that. Let's get a bit more into the technology behind it. So basically what happens is that a new news document comes in, or any type of document really, comes in and goes through a pipeline of a sequence of enrichments. These enrichments that we support in 15 languages to date are things such as sentiment analysis, of course. It's important to know what the sentiment around your product or brand is. Thematic analysis, categorization, key phrase extraction, and of course, what we will talk more about today, entity recognition and resolution, or disambiguation as it's sometimes called. And of course, the enriched documents then go into a storage, and our dashboard is really an application using that API for high-performance search. So we do obviously a bit of other things within my team, the data science team, other than just pure NLP. We, for instance, have built a recommendation engine that allows our users to fine-tune the analytics, the content that goes into the analytics of their dashboard. So a real-time recommender engine will look at the consumers' or users' behavior and determine how to fine adjust the specific set of documents that are important for this customer. We work on correlation and predictive pattern recognition, also for customer usage of actually knowing what will happen if it has happened a lot in the past. I won't talk too much about these. Another technique that we use a lot is word-to-vec techniques, where we map words into an abstract vector space, and enables us to cluster words and therefore do searches much better than just pure string matches. So these are just a couple of the technologies that we work with other than just pure NLP. But of course, our bread and butter is NLP and text analysis. Since a lot of you have a computer science engineering background, I won't dwell too much on this, but I thought it would be worthwhile to introduce some machine learning technology. I'm assuming a lot of you are familiar with what training and testing is, but essentially the type of algorithms that I will talk about here today and our industry predominantly engages with is what we refer to as machine learning algorithms that typically in the supervised case, and this is the supervised case, require a set of training documents with labels that represent whatever it is you are trying to achieve with the machine learning algorithm. And then you show the samples, the labels, so basically input, output to the algorithm, and then you ask it, given a new document, a new input, what's the label, right? It's almost like training a kid, right? You show them how to do something, and then you ask them to do it once or twice and see if they succeed. These sets are, of course, bigger than 1 or 2 examples. They're typically in the order of thousands or tens of thousands. So, what are the challenges with doing data science, or in particular NLP, at scale? Well, from a Meltwater point of view, of course, since we process billions of documents per month, social media documents, tweets, Facebook posts, Instagram posts, news articles, blog posts, we need to have a very high throughput. So the documents per second frequency that we typically require is about 2,000 documents per second, right? And there's a lot to do. So here's some NLP terminology, but there's things such as tokenization, lemmatization, stemming, part of speech tagging, categorization, of course, sentiment analysis, name identity recognition. All of these need to be done without any bottleneck, right? So how do you achieve that? And you, of course, have racing conditions, because when you start looking at these components, these modules, they all have dependencies. In order to calculate the output of one module, say the part of speech tagging, you actually need a noun chunker. You need anaphora resolution, for instance. So there are non-trivialities in doing that, in the sense that you can't just scale linearly. You can't throw more machinery at it. You actually need to do things in a certain order. So if we take the pipeline, that, of course, in practice looks more like this. There's lots of parallel pipelines that run on different instances, typically one for each language. Then, even despite that, certain modules need to fire before others. Certain things need to happen in order for other things to happen. So typically, as I said, part of speech tagging needs to happen before name identity recognition. And this, of course, becomes a challenge when you want to do things at 2,000 documents per second. Another challenge is, of course, training data. Training data labeling, what I just talked about, those sets of examples with labels, is costly, because you've got to have human experts for each of these modules that look at the document and do the work that you want the algorithm to do manually. And they need to do it many, many times, thousands of times, tens of thousands of times, and then multiply that with the number of languages that you need to support. A lot of money. Contextual information is, of course, expensive. If you want, a lot of these algorithms work in a way that if you want them to perform better, the more contextual information you have, meaning the more of the entire body of text that goes into the algorithm, the better they typically can perform. But that's computationally expensive. And of course, this is not necessarily something that just hinders you at scale, but noise, missing data, variation in the data. So for instance, for language, it's variation in language form and type, so slang, for instance. And data types, if it's news documents or patents or blog posts or tweets, it's all going to have very different variations. This offers a challenge too. So that's sort of the basic of NLP, at least from a Meltwater point of view. I would say it generalizes quite well to the rest of the industry. But what about the topic of today? What about entities? And where do these come in? Why are they so central in NLP technology today, in the NLP community today? Well, in order to answer that, we need to first understand what entities are. Named entities, as they're technically referred to, are referable entities, so entities you can name and refer to in a way, in any way. Usually it's proper names, so like Paris is an entity. It's a location entity, as it turns out. IBM, of course, is an entity. Gregor is an entity. Alexei is an entity. These are all entities because they have proper names, and it can be single word or multi-word. There's an example there. I know this man. He might be Charles. He lives in Stockholm. He's Swedish. There's a bunch of entities in that example. Now, named entity recognition is extracting these named entities, from natural text, natural language text. And you're categorizing these entities as you do that into a set of predefined categories or types. So these two steps, extracting and categorizing entities, is essentially named entity recognition. So John lives in Stockholm. He works at Ericsson. Would be, as this example, John is extracted as a person entity. Stockholm is a location. Works at Ericsson. Ericsson is an organization. Now, what's interesting about this is if you use your imagination and try to pretend that you don't know that John is the name of a person, that Stockholm is a location, or that Ericsson is an organization, you would still, if I replace this with X, Y, and Z, you would still be able to say X is probably a person, Y is a location, and Z is probably a company. So this is where we're starting to get at the core of what named entity recognition is and the value it can offer. So basically, in a text, all of the named entities need to be extracted for the sort of purpose of what we're trying to achieve here, and I'll get to that in a minute. So that's typically how it would look. It's also important to remember what named entity recognition is not, right? It's not event recognition, for instance. That's something that people typically forget or confuse. Named entity recognition does recognize entities in a text and classifies them in some way, but it doesn't create any template or perform any core reference or entity linking. Meaning, it doesn't know necessarily anything more about this entity than that it's a location, it's a person, right? It doesn't link it to anything else. That's what's usually called resolution or disambiguation, and that's sort of something that typically in entity recognition systems comes as an add-on, but named entity recognition itself does not offer that, right? It's not part of the definition of the problem. And again, as in the example of John, who lives in Stockholm and works at Ericsson, named entity recognition, it should say NER, is not just matching of text strings with some predefined database or list of entities, right? It's, as I said, you don't need to know from a database or a list of names that John, Stockholm, and Ericsson are entities. It only recognizes entities which are being used in the language, in the text, as entities. So it's the context that defines their identity. In other words, it's not easy, right? It needs to emulate how humans recognize unknown entities. So why do you want to do this? Well, of course, as you start thinking about it, you realize this is very central for structuring information, right? Extracting the good parts and knowing what those are, even though you don't know what they are, right? You know it's a person. It says a lot. You don't necessarily know who it is until you do some sort of resolution or disambiguation. So information extraction systems, this is the key part in them. Robust handling of proper names is essential for many applications, obviously. At Meltwater, we have examples of that. And it's used as pre-processing for different classification levels. We'll talk about that later today in a couple of examples. Information filtering, information linking, which is that disambiguation step, that requires entities to be extracted. And two things that I will talk about today: entity-level sentiment, which is actually a special case of this pre-processing for different classification, and the knowledge graph. Those are two very good reasons, for instance, to do entity recognition. So an example here is a German text here. You have the entities extracted, and if you do that properly, I don't know how many of you speak German here, you can actually start seeing effects, seeing bits and pieces of information expressed as entities that are decisive, for instance, for a company's stock. This is just one example of how the financial industry today, for instance, uses entity recognition. All right, so what about social? Why social a special case, or why is it even a topic of one of the topics of my talk? Well, social is obviously important because it's the largest body of user-generated content today. All right, so there's a lot of information in there, especially if you want to listen to data outside the firewall. Now, as it turns out, doing entity recognition for social is not trivial. All right, so it's going to get a bit technical from here on, but feel free to interrupt me for questions if you think it will help. But otherwise, I'll try to keep it simple. So how do you do, in order to understand why social is a challenge, we need to understand how you do entity recognition. Okay, so typically, entity recognition is done through what's called supervised learning. Again, so that means training data labeled, training an algorithm that learns to identify certain things, in this case entities, and then you test it. The typical methods that academia and industry, at least historically, has been using for this are these three types. Hidden Markov models is a way of creating probabilistic models based on what's called Markov models with some hidden variables that you assume dictate things. Conditional Markov models is a variant of hidden Markov models with what's called expectation maximization. And then conditional random fields, which is probably the most popular method of doing this, CRFs, use basically a flavor of hidden Markov models where you actually take the context, so sequence of data points around the data point you're trying to classify. So if it's a string, you want to say, is this a named entity or not? Conditional random fields are models where they actually look at the words around that string in the text. So they have a probabilistic model that takes the context, meaning the surrounding words, into account. That's all you need to know for now about these models. Training data is typically, as I said, it's ground truth data collected, labeled data, and it's expensive. The way you typically address this is you either have, at least for social, and this is what you will see in the state of the art in academia, you either do some sort of automatic named entity annotation using Wikipedia articles as training data, because there you have entities annotated. Or as we've done at Meltwater, you apply what's called LDA, latent Dirichlet analysis for NER detection using Gazetteers. And I'll come in a second to what Gazetteers are. But it's essentially list of predefined entities. So it's actually tables. When I said you don't use tables of lists of entity names, I kind of lied. There's such a thing called Gazetteers that help these algorithms, especially in a training phase, if you like. All right, so I'm quickly going to go through the pipeline, and here we're going to start getting into why social is difficult. But if we look at tweets, for instance, but this can be any corpora, so it can be editorial text, blogs. You typically have, and this is what you find in any sort of textbook about named entity recognition, you typically have a tokenization block that essentially breaks the sentence into the constituent parts that are semantically or in some other way relevant parts that belong to each other. So it's not necessarily, it's not necessarily that each word becomes a block. Several words can become one token, one block. And stop words and other things are taken into account here. In English, it's easy. You take the white space as sort of breaking most of the time. After that, you have something called feature extraction, which is essentially picking out the compressed pieces of data from your text that are relevant. So the most important part of that is probably the part of speech, POS, tagging, where you take out the grammar parts of your text. So typically nouns and verbs and adjectives and adverbs. And you actually also have a set of what's called closed classes of determiners, conjunctions, pronouns, prepositions that you also pick out. These all go into what's called the feature vector that describes your text. And after that, you have the CRF training that you've already sort of trained with label data, and your classification, or the model that is used for classification, takes all these features into account and then classifies those parts of the text that are entities as entity person, location, organization, miscellaneous. So there's a whole range of types of entities. There's a few different standards that have been set by the research community. But the 4 top ones there are the typical ones that you will see, and the ones that we focus on at Meltwater. Gazetteers, as I said, they help. They help a lot. It's, again, extensive list of specific names for a specific category. So for persons, it's first names, female and male, and surnames with frequencies. You can typically extract these for languages. For locations, it's cities, countries, of course, population. Organizations, it's name of companies from late yellow pages typically, right? So these help, but of course, as you can see, it's a costly thing, right? They're difficult to create, expensive to create and maintain, especially commercially, trust me. Their usefulness varies a lot depending on the category. There's ambiguity involved, of course. I have an example later of, Washington. Is that the person, the location? It can be a lot of things. Word occurs in so word can occur in more lists, right? Different types. Then there's something that helps here called Brown clustering. I think historically it's sometimes even referred to as IBM clustering. It was invented by IBM 30-odd something years ago, 20, 30-odd years ago. Brown clustering is essentially a way of predicting probabilities for things you haven't seen. Bigrams typically, but it can even be trigrams, so basically sequences of words. Let's say we want to estimate, and this is actually the problem that Brown, who at the time was working at IBM, was facing. Let's say we want to estimate the likelihood of, and I think he was working on the airline reservation system or something. You want to estimate the likelihood of the bigram to Shanghai. How likely is it that this sequence occurs? But let's say it doesn't occur in your training data, right? So what you can do there is, if you can cluster Shanghai with other city names, like London, Beijing, and you, for those city names, have the likelihood of, because you have seen those examples of to London, to Beijing, to Denver, then Brown clustering allows you to predict or guess, have a qualified guesstimate of what the likelihood of to Shanghai is without that ever occurring anywhere. So it's kind of an estimation or extrapolation of a probability that you don't really have real data for, real observations for. So Brown clustering, as I said, was proposed by Brown, 92, right? That was the year at IBM. It's sometimes referred to as a hierarchical class-based labeling method. It's bottom-up because it comes from the data. You don't impose that. You don't teach it. It's unsupervised, therefore. Doesn't require label data. It just requires lots of text to see the probabilities and frequencies essentially of different words and bigrams and trigrams. It's what's called a greedy technique, a greedy sort of maximization algorithm of the bigram mutual information. And mutual information, this is one of only 2 equations in all my decks, so don't get scared. But mutual information is essentially the log probability. So it's what's called likelihood also of the probability of seeing those 2 events. It says events here, but it can be words, right? Of X and Y and their individual probabilities. It's called the prior probabilities. It essentially merges words by contextual similarity. So if they occur in the same context. So let's take this example, and I'll get in a second to how we use Brown clustering. So large amounts of data is usually what's required. You have similar words appearing in similar contexts, right? That's the essence of predicting the probability for a combination of words when you haven't seen that combination. So similar words have similar distribution of words to their immediate left and right. So it occurs in the same context, similar context. So one good example is there and ah. They're both so-called determinants in linguistic speak. And you look at the frequency of immediate words to their left and right. So here, for instance, in, of, the, dog, part, store. So these, you can combine these in any way. So therefore, each of these are a cluster. Last, on, Tuesday, Monday, So these kind of naturally then belong to the same cluster, these words. So yeah, we can jump over this, but this is essentially how you do the clustering. So this sounds like easy then. I mean, so I've described the components, and you saw the pipeline. So what's the deal? What are the challenges in real life, in real applications? And what happens when you apply this to other languages? We've focused on English here, and does it equally well apply to, say, Chinese? Or, God forbid, Finnish? You will see in a second why Finnish is a God-forsaken language. I hope we have no Finnish people here, do we? And of course, social. What does that imply? Okay, so I mentioned this earlier in the example of Washington. So this ambiguation problem is, of course, something that affects entity recognition in reality, right? Washington as a string isn't always just directly identifiable. It depends on how it's being used, and that's sort of one of the challenges real name entity recognition needs to identify or resolve. So what is the category of Washington? Is it a person, organization, location, faculty, vehicle, geopolitical entity? These are some of the other ones in the bottom there are more exotic types. So of course in different languages then the challenge is, as I mentioned with Chinese for instance, words are not separated. So tokenization is not really possible, not in the traditional sense. Part of speech, so nouns and verbs, there's what's called inflection problems, which is conjugations for verbs, basically problems that you have irregularities and temporal tenses that don't exist in some languages and exist in abundance in other languages. Finnish, for instance, has over 10,000 forms of them. Actually does. You can take a verb and create 10,000 variations of it in Finnish, approximately. Or 1,000 variations, and then you can do that for about 10 different verbs in Finnish. And of course, you have what's called a shape feature. Capitalization is not the capitalization you would think of here. It's not capital letters. It's a linguistic term, but it's also a challenge. Here's a comic. I don't know, some of you may have seen this before. I like this because it really describes the Meltwater case really well. we are sprung out of Scandinavia, as I said, so Swedish amongst the other Scandinavian languages like Norwegian and Danish is a central language for us, and English, of course, is a central language. So in English, the English guy says, a dog. What's that, Brit? Says the Swede. The dog, 2 dogs. That's a few other forms of dog, right? The dog, it's still dog, right? A dog, the dog, it's still the word dog. It's not true in some other languages that you will see. So the Swede goes, oh, conjugation. Okay, I see. We have en hund, hunden, två hundar, hundarna. So in Swedish, the form changes if you use so if it's infinitive form or some other form. The German joins in suddenly and says, wait, I want to try too. No bugger off Germany, he says. Nobody invited you. And in German, as some of you may know, it gets even uglier. Der Hund, ein Hund, zwei Hunde, and then Hund, einen Hunden, dem Hunden. So you have variations. And then the Finnish guy comes and says, hey, Sweden guys, can I join in? 9-9, they get all really upset. And then he starts listing the different inflections of dog in Finnish. So koira means dog, but then there's koiran, koira with 2a, koiran again, koirasa, koirasta, and then he goes on. And actually, each of these forms is a real one. These are all inflection forms of dog in Finnish. Yeah. And that's just the singular forms. And in the end, he goes, oh, and now for the plural forms. Yeah. So languages can be tricky. And study of the linguistic properties of each language cannot be taken for granted. You can't just rely on the algorithmics to do it for you. There's a lot of confidence today, of course, in deep learning and then some other techniques to sort of be the holy grail of machine learning, the ultimate black box in which you can throw everything and it does magically solve any problem. Linguistics is probably the best example of why that can never be perfected in an unsupervised way without linguistic expertise. So, I've been promising that social is something we're going to talk about, and social is in fact tricky. The more you move towards user-generated content, typically for a lot of these algorithms, not just name entity recognition, performance drops. And it does so for the reasons we all kind of know, right? It's unstructured language. If we take tweets, for instance, and use some off-the-shelf, say, name entity recognition, but it could be anything, really. It can be sentiment analysis. It can be categorization, you name it. Tweets are short, of course. We know that. We know that they're in those 140 characters cover a whole universe of topics. They're typically not written in any humanly recognizable grammar, typically written by people who don't even know grammar, meaning children, kids. And they're written fast and posted anywhere. A lot of misspellings, and people don't really care about them being misspelled because humans kind of can deal with that. So if we focus on name entity recognition now for a moment, we would need a solution that considers social characteristics of text, some of which I've listed here, right? Now, examples of noisy data, yeah, I mentioned these. You can have misspellings, OMF instead of OMG, and not because, OMG itself isn't even a word, right? But you would need to be able to resolve that. So yeah, hashtags, of course, at mentions, retweets, multi-word abbreviations, and to put it mildly, non-standard spellings. Okay, what's our solution? Well, at Meltwater, we've developed an in-house solution to this that at the core really relies on adapting existing features. So we tried a lot of exotic approaches to this that are in the academic research corpora. But ultimately, we found that adapting existing features to social properties is the way to go. And this is a work that we've published at a famous NLP conference about a year ago. And we've mainly focused on the post tagger, but also the brown clustering that I mentioned. So there we have a lot of course, in terms of tweets, you have a lot of just raw text data. And as you remember, brown clustering is unsupervised. You don't really need labels. You need to see what words typically occur with what other words. So that helps you, especially with these sort of self-invented words that you have in social. Okay, I promise you another equation. This is the last one. This is a CRF. This is the mathematical formula for a CRF. What you typically try to estimate is, or learn is a model that consists of a set of weights, these lambdas, over features that you have. So these can be part of speeches and you know, tokens in the text and features that come from the brown cluster. So once you've identified a word, you kind of identify which cluster it belongs to in your brown cluster, the tree that I showed you. These are sort of the features that you could gather from the text. And what the CRF essentially does is that it's maximizing the conditional likelihood, which is this. So it's, you know, basically it says what's the likelihood of getting the output I'm getting given a set of features. Right? So it's trying to determine what feature weights it needs to maximize what it's seeing. The features that we use are 35 features, and it's basically these types. We call them internal and external features. And as I said, it's the tokens, it's the post taggers, it's the brown clusters, and it's features coming from the Gazetteer matchings that you have from the text. So you throw this into a big, nice soup, and you get something like this out, right? You get the weight importance of each CRF feature as a result of your training. Right? This is for all those 35. And as it turns out, when we have tested this, it outperforms state of the art. State of the art is by this guy at University of Washington, I believe. I don't know if he's still there, Ritter. That is the orange one. Well, it's actually the blue one there and the orange one. But we significantly outperformed Ritter on this. Of course, we had a lot of training data. 76,000 tweets labeled by human annotator. And this is English only. You can do the math of how much that typically would cost. And we require what's called an inter-annotator agreement of two annotators. So we need, on the labels, we don't trust one labeler. We want two labelers to say the same thing independently about a label, to say, okay, this is the correct label. So that's sort of guaranteeing a certain level in the labeling. And then test data is about 9,000 of those, or an additional 9,000 actually. Okay, so right now we have a way of doing name entity recognition for editorial and kind of cleanly written text. We have homebrew of how to do it for social text, which is a bit more challenging. And we believe we can do this at an acceptable level. Why do we want to do this? We talked a little bit about, at a high level, information extraction systems and some of the other things I mentioned. But essentially it comes back to, you know, from a Meltwater point of view, identifying entities in a business context, right? Pepsi here spooks Coke with ad, a Halloween theme ad. And you kind of want to know what's going on here without having to read all of that content out there. And for that, you need to identify these entities, of course. And specifically, after this ad, there was a lot of sentiment in social media going on around Pepsi and Coke. I don't know how many of you have seen this or heard the story behind it, but yeah, it caused a lot of people weren't really sure who was spoofing who unless they saw this. But yeah, there was a lot of sentiment in social media that both Pepsi and Pepsi and Coke were interested in tapping into. So for that, you need what's called entity-level sentiment, which is the second part of my talk. So what about sentiment, and why is entities important here? Well, if you look at sentiment, how it's traditionally used, you have a document, and you have a human looking at it, and you ask them what's the sentiment in this document. This is what the industry typically refers to as document-level sentiment. And this kind of works. The human reads it and says, oh, this is a positive text. And unfortunately, it applies equally, the method applies equally to whether it's social text or blog or news article. But then you show the text to another human, and that other human says, oh, no, this is not positive, this is just neutral. And likewise, a third person might say, no, this is actually negative. What do you mean? It turns out, when you do this exercise, and there's studies that have shown this, the typical inter-annotator agreement is about 80%. Doesn't get higher than that. So on average, humans only agree when it comes to sentiment. And this actually is a sort of red thread for a lot of the NLP stuff we're doing. Some of it is, the annotator agreement is, where's the punctuation in the sentence? People typically agree on that very highly. But some of the other things like sentiments, not so much. It's subjective, right? Why is that? Well, I'll get to that in a minute. Before I do, so how is this used then? Well, in machine learning and in NLP, what you do is you somehow gather human labels. You have annotators who are agreeing. You use only those documents, for instance. And of course, you gather lots of them, thousands and thousands. And then you feed them into your magic box, machine learning magic. It's typically some sort of supervised learning, right? I've listed a couple of them for those of you interested. Naive Bayes. So Bayesian methods, support vector machines, of course, maximum entropy models, multi-layer perceptrons, so deep learning neural networks. But really, it doesn't really matter what method. Once you've trained the model, the expectation is, OK, I feed a new document into it, and it tells me the sentiment. Woohoo, yes, we have a solution. Let's put it into production. OK, we put it into production. And it turns out the accuracy is somewhere around 60 and 70. And OK, granted, this is not too terrible, given that the human annotator agreement is at best 80. But why is it so hard? Why don't humans agree, right? What's going on here? Is it something fundamentally wrong with how we perceive sentiment? So at Meltwater, for instance, we have the document sentiments, and we gather them into one of those dashboard analytics. But if you look at one of these documents, it might shed some light into what's going on. Let's take this article here. I think the article came out as negative. All right, so it talks about these politicians. It talks about Rudy Giuliani and Scott Walker in a very negative way, clearly, when you read the text. But then you see that it talks neutrally about this guy, Obama, and you wonder, so what's the sentiment of this article? It clearly depends heavily on what your perspective is. Are you, a Meltwater customer, someone on the Obama campaign? Well, then you would say this is a neutral document. You don't really care about what it says about Rudy Giuliani or Scott Walker. If you are the PR responsible of Rudy Giuliani as Meltwater customer, then you want Meltwater to tell you this is a negative document. How do we solve that? How do we tell that a document is negative and positive at the same time? Another example here, McDonald's in this, it's a Facebook post, I think, is negatively mentioned. These other companies, Panera Bread, Chick-fil-A, Chipotle, are mentioned positively. So when you look at a text, just like I showed with the politician, the Rudy Giuliani or Obama text, you will find different entities in there mentioned in with different sentiment. And that's why when different people look at it, they perceive it as different sentiments. So when you feed the whole document into any algorithm and ask it to give you one answer, it's not going to satisfy all three. And on average, it's going to be wrong. Well, as I said, the best algorithms today are about 60, 70%. So this approach, document level sentiment, I argue, doesn't make sense for our industry at all. In comes entity level sentiment, therefore entities, right? So clearly, there's something here that depends on the entities. So we've established that document level sentiment is imprecise and wrong for our customers. In this industry, entities are of main importance for our customers. We already have named entity recognition technology. So here's a crazy idea. Why not identify the sentiment towards each particular entity in a text? So you run named entity recognition, you get the entities, and then you ask a human not to tell you the sentiment of the text, but the sentiment of each of the entities in that text. All right? As an example, BMW positive, Mercedes neutral, Toyota negative. And of course, you do this lots of times. Again, some sort of machine learning box. And a new document comes in, you run NER, and what the machine learning box gets as an input is a document with named entities identified. And you ask it what is the sentiment towards each of these, because it's already been trained with that. And it tells you that. So I'll jump ahead here. We've done in-house technology around this. We've explored and benchmarked a bunch of vendors of this technology out there. It turns out it's really difficult. I won't get into the nitty-gritty of why this is still difficult. I mean, you could argue that, hey, accuracy should be higher now that we have separate entities and stuff. But it turns out introducing this additional level of complexity of actually identifying entities, which itself can be, well, it's not 100% accurate, right? And adding that into the equation of then doing sentiment just isn't really there yet. But my belief and my hope is that if the industry, if the research community focuses on this way of tackling the problem instead of the sort of the old way of just taking the sentiment of a document, we will see progress a lot faster and a lot more than we have seen in the past 20 years with just traditional sentiment. Okay. I know how I'm doing with time. All right. I'll speed through this. The other reason, from a Meltwater point of view, why we are so excited about entity recognition, besides doing proper sentiment analysis, is what I call the holy grail of really business intelligence at large, the graph knowledge base. And here, we're not just interested in the entity, in the sentiment towards entities. We're interested in the complex network that these entities live in, which is the real world, right? So these companies, or organizations, NGOs, these people, or journalists, bloggers, key employees at companies, C-suite level people, these products and services and brands that we have around us, all of these have relationships to each other, right? A product is a product of a company. A person is employed somewhere. He's friends with some other person. A company is a subsidiary of another one. Another company is a partner of another one. They all have relationships, and there's a connectivity in here that's rich. And all of this is kind of exposed through the sometimes narrow, sometimes wide window of media. Social media, news media, blogs, tweets. All of these talk about, in one way or another, in the order of billions of documents per month, these relationships. They talk about something happening, someone acquiring someone, a company releasing a product. So it's all out there. And if we have the building blocks, the tools of extracting these pieces of information, the entities being the core of this network, then why not attempting to build this ourselves? So really what we do at Meltwater is that we introduce in this architecture thing I showed you earlier, we introduce this component here that we call the graph, where those 2,000 documents that are swooshing through our pipeline communicate and talk to this graph, tell it stuff, and ask it stuff. Right? Why is this hard? I mean, okay, that sounds like, okay, that's it, we've solved it. No, it's hard, and it's hard for these three reasons. Data, scalability, and the new features that this requires. Relationship extraction just being one of those. So data acquisition is difficult because you basically have this trade-off that you need to manage, right? In this pyramid here, on the top you have low quality. At the bottom you have high quality. So low quality is typically special crawlers, smart algorithms that you can use to harvest the data from websites and whatnot, but you don't get the richness of a quality that, for instance, a human could give you if they list all the properties of IBM, number of employees. What kind of like TechCrunch does in the crowdsourced way. They have a lot of information about each company, or LinkedIn. It's high quality, but what it also is expensive, unless you come up with some smart way of doing crowdsourced, like TechCrunch and LinkedIn does. So in this end, you have expensive and cheap. Expensive, of course, acquisition and partnerships. Low volume, high volume. Manual acquisition is a way of doing it. You get the quality, but it's expensive and it's typically low volume. So you can't have all three. So whatever you do, you get a point somewhere in this triangle. That's one of the challenges. The other challenge is, of course, scalability. We're talking about, in the world, in the order of typically 100 million companies, 500 million people. If we only focus on the key individuals in these companies, and not all the social influences and what else that's out there. It actually should say excluding media influencers. Sorry for that typo. And products, let's say in the order of 500 million. This is a lot of entities. That means we have about 1 billion entities with all the connections between them, theoretically speaking. So billions of nodes and trillions of edges on an average order. This is a scalability problem that is in the order of magnitude of what Facebook faces. And third challenge is, of course, new features. And I will jump through this really because it's not that interesting, and actually jump all the way to the end. Okay, thank you. Yeah, let's open up for some questions. Andrew.
Yeah, you said relationships before. What kind of relationships are they? Like, do you have a predefined set of relationships? Because a relationship can be anything. There's so many different types of relationships. So how do you define what relationships you're going after?
Right. So the question is, how do you define what relationships that are interesting? I think it's something that needs to be very business-centric. For us at Meltwater, it's typically the relationships that our customers are interested in. So I mentioned a couple of examples of that. It's companies having partnership, subsidiary, competitor relationships to each other. It's products being competing products with each other. That's a relationship between product and product. And then, of course, products being products of a company. If we include influencers, as we're looking at doing it, then, for instance, an influencer can have the relationship to a product being he's an influencer, he's an important voice when it comes to, say, iPhone 6, right? That's a relationship. And then, of course, between people, there's relationships, network relationships. But it really needs to be dictated by the business requirements that you have with your graph, with your knowledge graph. Yes?
So you mentioned the word-to-back representations.
Yeah.
Are you being able to use that to replace any of the feature engineering, or do you use that?
Yeah, good question. So the question is word-to-vec. That's a recently emerged approach that was, I think, pioneered by Google. If we use that in Meltwater, we do. We've more or less successfully used it for categorization because the unsupervised strength that word-to-vec that basically maps words to a vector space where you can actually do math with the words, and you can actually say, you know, what is Paris? What's Paris to? What does Paris correspond to if London corresponds to UK? And then you expect it to say France because of the vector relationships. This kind of, you know, arithmetics with words allows you to do, for instance, document categorization much more accurate. That's what we use it for.
Oh, okay, so you get basically like a smaller space that is easier.
Much smaller space, because you can suddenly start cluster things, and you have only the clusters to take to care for rather than individual words.
Sorry.
Yeah, of course.
You haven't really used it to replace any of the NER stuff.
For the NER stuff, no, not yet, no. Yes?
It's a newbie question. So how do you contrast word-to-vec to, say, conditional random fields? I thought they were both kind of linked to concept issues words.
So I think the question was how I relate word-to-vec methods to, what was the? Conditional random fields. Really, it's in the way those classes are. They're essentially achieving the same thing. Word2Vec offers a much simpler way of achieving that. Like the matrix algebra of calculating the Word2Vec relationships is much easier than solving a conditional random field equation, because that would require label data. Word2Vec approach doesn't require label data, right? So it's the simplicity that it offers, really.
So what was novel about getting stuff to work with like the tweets? Like, was it just changing the training data, like training exclusively on like social media data, or did you like have some?
So essentially, and a lot of that is in the research paper that we published. It was essentially to add additional features. So you know, I showed you that some of these abbreviations and things that occur in social text, they need to be taken into account. And if you just run a standard off-the-shelf, say, tokenizer or basic lemmatization, a lot of these things might be thrown away, for instance. But if you have features that really take the social characteristics of social content into account, you can use pretty much the same models. And then the other thing that is special is the Brown clusters that need to be retrained for social text.
So you use the same core models for social text, but you use some pre-processing approach?
Yes, basically, yeah. Yep.
Have you open sourced any of your algorithms?
We have not. We haven't yet, I should say. That's something I'm personally working on. It requires buy-in from my boss, basically, and the stakeholders in the company. But we're carefully deciding which parts of our code base that can be open source. But we intend to.
So we went over the named entity extraction, recognition. I guess
Okay.
Where does that fit in?
So named entity extraction or recognition is essentially about non-dictionary based, minus the Gazetteers, non-dictionary based recognition of entities, right? Being able to say this is a company without having a database or a knowledge base that tells you it is. Disambiguation can be done really in two ways. One is to resolve it against a knowledge base, right? The other one is if your body of text is not just a small tweet or a small document, but a large document or maybe a bunch of documents in which, I actually speeded through that example. So for instance, IBM, Big Blue are mentioned. They're clearly referring to the same entity. A human can identify that. Maybe not so much without knowing about IBM and Big Blue, sort of terminal, or the term Big Blue to refer to IBM. But still, some context you can actually realize, oh, this is probably the same company it's talking about without knowing what that company is. So that's unsupervised disambiguation, where you basically cluster within a large body of text references to the same entity. But typically in the industry, disambiguation is done by reference to some sort of external knowledge base. Wikipedia is a good one, Crunchbase, LinkedIn. These are, of course, not commercially available except Wikipedia. But yeah, that's the essential way. You first recognize and disambiguate against a database, knowledge base. Other questions?
Do you guys create your own web crawling packages?
Web crawling, we do not. I mean, we have small projects in-house where we do web crawling for other purposes. But if you're asking for the purpose of the knowledge base, we do not. If you mean for the purpose of gathering news articles and whatnot, yes, absolutely. We have our proprietary crawling technology for news websites. We have about 150,000 news sources. Google News, in comparison, has 40, 50,000 news sources. Okay. If no other questions, then thank you.